In this video, we'll talk about the semantics of predicate logic and how to interpret well-formed formulas in predicate logic. There's a lot of technical stuff on this paper here. Basically, I'm just going to summarize this in casual terms, and if you're interested in the further details, you can read about it. But we're not doing semantic trees for predicate logic well-formed formulas like we have in the end of the slides, so we don't really need to care about this in too much detail, but it's there if you want to prepare for the actual sentences in lecture 8. So basically, we're talking about meanings of terms, predicates, and so on. So if alpha is a term, it's either a constant or a variable. If alpha is a constant, it basically just gives out the denotation of who that person is. So we use this function v and we apply it to alpha, and then we get, say, a person. So if alpha is going to be a constant, it probably references some person, so it gets this person. But we can also give them names just for convenience. So this could be a lowercase letter like John, or it could be a J prime, or it could be the name itself. But a constant gives a person. If we have a variable, it takes our assignment function and just runs it through that assignment function. So let's say we have some variable x. We want to know what x is. Well, we go through the assignment function g, and g will tell us, well, x, y, z, and a bunch of things. They map to different things. So whatever x goes to, let's say x goes to f, then that just pumps out an f. Typically with assignment functions, we check them at the end of the derivation, at the end of the tree, and we'll see that explicitly stated in lecture 8 when we talk about the truth conditions of quantified sentences. If we have a predicate, so this is a word like likes, we know that in terms of set theory, likes is a set of pairs xy, where x likes y. So when we check the value of likes, the predicate itself, basically what we get is we get a set of pairs. So these are all the set of pairs where we have x, y's, where x likes y. So maybe we call this x1, y1, x2, y2, x3, y3, and so on. If we have a n-ary predicate, so this means that if we have something like likes xy, well, this is like a sentence, right? Likes xy. So we say it's true if we have xy in likes. So basically, remember, likes is a set of pairs. So likes xy is going to be true if xy is in that set of pairs. So this is what the semantics of terms and predicates are. When we go to the well-formed formula stage, so we have full predicates and we have connectives. We have our connectives like we did before, so this is the exact same as propositional logic. The only difference is that instead of v, we now have m and g. M is a model, and g is an assignment function. The model is basically a universe that consists of things. So you can think of a situation as things being true or false, but models consist of people and actions. And assignment functions are, of course, assignment functions. They will map our variables at some point. So for connectives, not and, or, if, then, and if and only if, nothing is different from propositional logic. It's just that we have the difference between v and mg. However, with quantifiers, this is where we use assignment functions. And I want to explain quantifiers a little bit differently first. So when I say something like all x px, imagine I have a universe with 3 things in it, 1, 2, and 3. If I say for all x px, what has to be true? Well, that means everything in the universe has to be p. So we need to know that p1 is true, and p2 is true, and p3 is true. Because we need to check everything in the universe, and everything has to satisfy that condition for all x px. Similarly, with the existential px, we have to run through everything in the universe. But the existential just says one thing, not one thing, at least one thing is p. So there is some x that is p. So we need to check either p1 or p2 or p3. And one of those has to be true for existent x px to be true. So regardless of what our universe is, if it has an infinite number of things, it has to go through each of those things to check. So if the universe has a million things, for all x, px, a million of those have to be true. If there exists an x, px, at least one of those million things has to be true. So what our assignment function does is it basically gives us a dummy variable. So if I say, again, for all x, px, I need to check P1, P2, P3, P4. I need to go through the entire universe. So what happens is we do this thing and we say PD. Okay. Now, what PD is going to do is it's going to run through the universe. It's going to check everything. This is like a dummy variable. It's being bound by the x initially. We use an assignment function to replace it, and then we check everything in the universe. So I explained that before I talk about these definitions. So let's do A. We say for all v alpha, and an assignment function is true, if alpha, where v is now pointing to d, is true for all individuals d in our universe. Basically, we take v, we reassign it to d, and we say, okay, I need to check every single individual d in the universe, and that has to be true for every single case to be true for all v alpha. So this is just a fancy way of doing this thing above, checking everything in our universe. The existential is very similar. There exists a v alpha is going to be true if alpha, where now we have v pointing to d, is true for some individual d. So we check d, so we check 1, we check 2, we check 3, we check everything in our universe, and as long as at least some individual has that property, then it'll be true. So this is just a fancy way of describing this process right here. And we'll see this in action when we start, of course, truth conditions of quantified sentences. This is really all preparation for that. So we'll see how that works in action. But in terms of actually analyzing well-formed formulas to see if they're true or not, you can just use this method I showed you in the top right that's highlighted, checking everything in the universe. Okay, so the reason we have this assignment function thing is to bind variables. So we can bind any variable, and then we can use that binding to check everything in our universe. So imagine we have some model here. We have the universe, ABC. So these are the elements in our universe. This is what we have to work with, ABC. We have A, which is AB. So basically this means that A is some predicate. So let's call this A. And A of A is true. A of B is true. And our third element, A of C, is going to be false because C is not in that predicate A. When we think about this R, this has pairs. This is another relation, but this is a transitive relation. So basically this says that RAB is true because AB is in R. This also says then that R of AA is false because AA is not in R. And R of AC is true because AC is in R, and so on until we get to RCC, which is the final one, and that's also true because it's here. So these are just relations and sets disguised in predicate logic. So let's determine the truth values of each of the following formulas, referencing our model here with the universe and our relation A and our relation R. So the first one says RAB and RBB. So this is saying is AB in R and is BB in R? Well, RAB is an R, which we see right here, RAB, but we don't see BB in R. So this is 1 and 0, which of course is the same thing as saying that it's false. This is just propositional logic at this point. Okay, B, if not AC, then RAC. So first, we check the value of AC. Well, according to what we've seen here, we take a look at our description, C is not an A, so AC is false. This means that not AC is true, since, yeah, it's not the case that C is an A. then our AC. Well, is AC and R? Yeah, I see AC and R right here. So our consequent is going to be true in this case, which means that our result is going to be true. Okay, so this is just checking predicates on their own. We don't have quantifiers here. Let's do quantifiers now. Things get a little bit more complicated. So C says, for all x, Rxx. So for all x, what this means is we need to check everything in our universe. We need to plug every element in our universe into x and see if it's true. So we need to check three things. We need to see, is RAA true? Is RBB true? Is RCC true? Because we're saying for all x, Rxx, all of these have to be true for this to be true. Well, CC is an R, as we can see right here. But BB is not an R, and AA is not an R. So for all x, we do not have Rxx. It's only the case that we have RCC. We don't have RAA, we don't have RBB. It's not reflexive if you remember that term. So C is going to be false. Let's check the next one. And we can actually just modify this a little bit. For all x, if Rxx, then not AX. Okay, so we need to check the cases where x is everything in the universe and see what happens. So this is going to change to RAA, if and only if not AA, RBB, if and only if not AB, RCC, if and only if not AC, and let's check some truth values. So I'm just going to do the arrows in black, and we'll do the truth values in red and green as we did before. So let's move that to the side a little bit. RAA. Is this false? AA is not an R. What about not AA? So we're saying it is not the case that little a is in big A. Well, actually, we know that AA is true because we see A is in our relation A, therefore not AA is going to be false. This is 0, arrow 0, so this comes out to be true. Okay, RBB, well, B, again, the pair BB is not in R. If we take a look at B, is B in A? Yes, it's in A, but that means that B is not in not A. So this gets the same result as our first line. So this is true. And again, to get not AB, I'm checking the value of AB. I know this is false. I'm negating it, and that's making it true. So I just do that in the top left. Sorry, I got that backwards. AB is true, therefore not AB is false when we negate it. So that's why we get a 0. The same idea, I just got the truth and false mixed up. Okay, finally, RCC, then not AC. Well, RCC is true since CC is in R, and not AC is true, and that's because we know that AC is false. Therefore, when we negate it, we get not AC is true. So in each of these cases, with the biconditional, we have 0, arrow 0, 0 if and only if 0, 1 if 1. All of these are true. Therefore, the universal statement is true. For every x in our universe, Rxx if and only if not AX. So we have to check each of those conditions. Now, this last one, a little bit more work involved. There exists an x, there exists a y, there exists a z, such that Rxy and ay and Rxz and not az. So two things to note. One, when we have a bunch of ands or ors strung together now, we don't need to put the brackets in to separate them. We know it's commutative, we know it's associative, so we're just going to say that in our syntax now. We can just put these all side by side. So this is fine for us at this point. Now, exists an x, exists a y, exists a z, such that this all is true. In order to say this is true, we just need to find one situation. We just need to find one situation that's true. So we're going to have to make substitutions for x, y, and z to try to force this to be true. And if we can force it to be true, then this will come out as a true statement. Okay, so one thing to remember is x I'll write this out first and I'll explain it. Okay. X can be Y can be Z, which means that we could do, in fact, maybe this is a better way to do this. We can do something like X is A, Y is A, and Z is B. This can be fine. We can substitute two different variables with the same thing in our universe. That is acceptable, or they can be all different. So what I'm going to do is I need to make sure that this is true. So I'm looking at this not AZ first, and I'm doing this because I know that I have one variable, or sorry, one constant that is not in A. I know that C is not in A. So what I'm going to do is I'm going to make an initial assumption where I replace all the Z's here with C. So I'm going to actually rewrite this without the constants inside, just to see what we have here. So I'm going to make the substitution where I have not AC, because I know that's true. I know this is true. And I'm trying to make this true to prove that this works. Okay. Well, now I need to pick an X and a Y, so I have to be a little careful with this. I need RXZ to be true, so I need something in C to be in there. But I also know that whatever I pick in RXZ, it's also going to be the first thing that is in RXY. So I need to take a look here and say, okay, I see C at the end in two positions. So I can either pick X to be A or I can pick X to be C. I have a choice here. But whatever I pick to be on the left side, so whatever I pick to be X, I'm going to eventually have that in a pair with Y. So I think for safety, I'm going to pick a different variable. I don't know if it's going to make a difference, but I'm just going to pick A for this and see what happens. So let's say that X is A. Okay, so now I know that RAC is true. It's in our set. I need to find something now where RAY is true and AY is true. So I need to pick something for Y where this works. If I pick Y is equal to B, then I get RAB and AB. Both of these are true, so the entire thing works out. So to do this, I had to basically substitute in my three variables with constants. I chose X to be A, I chose Y to be B, I chose Z to be C, and it turns out we can find a situation where all of these are true. This says there exists an X, exists a Y, exists a Z, such that all of these are true, which means I just need to find one configuration that works. I did find that configuration, therefore it's true. So normally, something like E is quite complicated and we don't really ever work with this stuff. I just wanted to show it for the sake of like, this is how you can do it if you see something with three existentials. Normally, if you look in the real world, you have some English sentence or you have some situation, and it's much easier conceptually to think about these things and to make substitutions for X, Y, and Z that make sense because you have something intuitive in the real world to map it to. In this situation, there's nothing really intuitive here. This is all arbitrary, so it's a little bit harder to determine what X, Y, and Z are, but it's possible to do. You're much more likely to run into situations like A through D, which are a little bit simpler to figure out. They have a little bit less guessing and checking. Anyways, that's how we interpret PC Wffs. On your assignment 5, which is due next week, question 3? Which question is it? I think it's question 3. You're given stuff about English letters, so consonants and vowels, and you have to determine whether the statements are true or false. So this is the type of, or this is the approach you would take to solve that question. Anyways, as always, if there's any questions, discussion board, email, I'll answer you.